Hello. Today we're going to talk about the Michelson Morley experiment and what it means regarding the propagation of sound and light. Here's the disclaimer. The material is based on sound scientific principles. The opinions expressed here are mine based on the observations we are going to make. The presentation has not been peer-reviewed or accepted by any journal. The information in this presentation is general in nature and not intended as professional guidance, nor will it assist you in passing any exams. You're encouraged to confirm any information obtained from this presentation with other sources, and this material is copyrighted. In the previous two videos, Physics 1 and Physics 2, we learned how distance affects the display, the delay of signals for stationary or moving sources. This presentation will discuss how an interferometer can be used to measure path length differences between signals. We will discuss the concepts of ether and length contraction and how they were used to explain the results of the Michelson-Morley experiment. We will then tie this back to the Doppler effect and present a new theory for the definition of the speed of light. More than a century ago, there was much debate as to whether light was a particle or a wave. The ether was proposed as a medium for carrying light waves just as sound travels through air. Scientists at the time thought that the motion of the Earth through this ether could be detected using an interferometer. An experiment was devised by Michelson and Morley in the late 1800s. This material was compiled from Britannica.com. The interferometer was constructed like this. A partially reflective mirror splits a beam of light, allowing some to pass through to a fixed mirror, path A, and some to be reflected toward a movable mirror, path B. These beams are reflected and returned to the partially reflective mirror, where reflected beam A is reflected toward a screen. Part of reflected beam B also passes through to the screen. These two beams combine, producing an interference pattern on the screen. The movable mirror is adjusted to calibrate the pattern, then locked down so that the pattern is fixed. If the path lengths are the same length, they add, producing a bright spot at the center. Otherwise, they tend to cancel, producing a dark spot at the center. Concentric bands of light and dark rings surround the center of the screen. The interferometer is then rotated to sense a change in the interference pattern, such as might be observed by the movement of the Earth through the ether. The rings should move in or out, indicating a change in path length due to waves passing through a moving medium. It was expected that light moved through the ether like sound. This plot is a reasonable representation of sound moving through air. Since the air is not moving, the sound waves will bunch up as the source moves through it. In the graphic, the blue dashed lines illustrate that each wave emanates from a fixed point of origin and spreads out spherically through the medium from each point that the pulse originated. This was the expected behavior of light from the interferometer as the Earth moved through the ether. The direction of motion of the Earth should have been detectable as the device was rotated. Because the number of waves per unit length was different in each direction, the interference pattern should change as the interferometer was rotated. When one of the arms is moving in the direction of motion, more waves should be measured. Fewer waves should be measured when one of the arms is in the opposite direction. The pattern on the screen did not change when the device was rotated. The test failed to detect any motion through the ether. Einstein concluded that the speed of light was a universal constant and that lengths contracted in the direction of motion. This is what length contraction would look like for this severe Doppler case. The lengths must adjust to maintain an equal phase. One of the difficulties with relativity in the literature is that the speed of light is always given as a number, but the speed must be with respect to something, because that is the nature of relativity. Is the speed a constant with respect to the source, the observer, or something else? Whatever it moves with respect to, it has been deemed that it have the same value no matter what. Physicists would have us believe that every observer, no matter what their velocity, measures the same value for the speed of light. Between this and length contraction, there are an awful lot of gyrations being made to maintain the wave nature of light. We will explore these concepts further in future presentations. I propose here that light moves uniformly with respect to the inertial frame of the source, that light travels at v plus c, meaning the velocity of the source plus the speed of light. This theory does not require length contraction and fits the results of the Michelson Morley experiment. One nagging possibility might be that if there is an ether, some of it is dragged by the Earth like a fluid. Fluid dynamics suggests that there is a layer of fluid that stays with the boundary. In this illustration, the fluid velocity is 0 with respect to the cylinder walls. A velocity gradient exists for the fluid away from the walls. This applies if the fluid is still and the cylinder moves, or vice versa. If the walls were the Earth, it is possible that an ether could be dragged locally with the Earth, preventing us from seeing movement through this ether. But this seems highly unlikely to me. Let's derive the Doppler equation for a moving source with respect to a stationary observer. The equation for the signal from a moving source is omega t minus kr minus kvt cosine theta, where just like before, omega is the radial frequency, t is the time, k is the wave number, and r is the distance from the source. For the source movement, we added a term where v is the velocity of the source, and theta is the angle that the observer is from the direction of motion with respect to the source. This is like the equation we developed in our previous presentation, Physics 01, except we have added a term describing the motion of the source. We can regroup the terms so that omega t times 1 minus v over c cosine theta minus kr, since k is omega over c. This is the traditional representation of the Doppler effect, showing a frequency shift due to the motion of the source. The origin of each sphere occurs at the point at which it was emitted, just like we saw for the ether example a few slides back. An alternative representation is omega t minus k times r plus vt cosine theta, where we regroup the original terms with respect to space instead of time. This equation represents a spherical wave that moves in the x direction. The origin of all spheres moves with velocity v, just like we saw for the graphic without ether. These are equivalent expressions for the signals from a moving source. One shows the effect on frequency, the other shows the effect on wave velocity. They look the same at the location of the observer. In summary, the Michelson Morley experiment implies that the speed of light should be measured with respect to the source. If you found this presentation interesting and/or informative, please like and subscribe. Thank you.